Hello everyone. Today we'll continue with sets. In this class, we'll cover some important formulas of sets. For the first formula is A minus B union A intersection B is equals to A. From the Venn diagram, I've shaded A minus B t-shirt with pink line. A intersection B is green shaded region. By observation, this covers the whole set of A. Hence, A minus B union A intersection B is equals to A. In terms of n of A, which is number of elements in A, the name itself suggests that it is a number. Number means numerical value. Same formula can be converted in terms of numerical values, but instead of union, you'll have to place an addition. Because this is algebra, you're adding two numbers. You'll get a number value, n of A. Second formula, B minus A union A intersection B. Now uniting the yellow part with green part, you'll get the whole B region. In terms of number of elements, it's n of B minus A union n of A intersection B is equals to n of B. By this, we observe that union in sets, in operations of sets, is analogically equal to addition from algebra. Similarly, intersection will be analogically equal to multiplication in algebra. The third formula states the union of these three shaded regions, pink, green, and yellow, or A minus B, A intersection B, and B minus A. We'll get the whole region A union B. In terms of number of elements, it's n of A minus B union n of A intersection B union n of B minus A is equals to n of A union B. The next formula is n of A union B. You're deriving a formula of n of A union B. We make use of all the three formulas that we just studied to derive this formula algebraically. But first we'll see how we can come up with the formula of this n of A union B using Venn diagram. In the Venn diagram, adjacent to this, A region, the whole of A region is represented by dots, and the whole of B region is represented by pink lines. Now, by observation, if you want A union B, you'll have to cover both the regions. So let's add the two regions, n of A plus n of B. What happens over here? This region, n of A intersection B, is covered twice. We need it covered only once, so you'll have to, by default, remove or subtract. Thereby giving you the formula for n of A union B. So n of A union B is n of A plus n of B minus n of A intersection. You can also prove the same formula using algebra. So let's consider the RHS first. N of A plus n of B minus n of A intersection B. Now we have the formula for all these three values, all these first and two values, n of A and n of B, the first and second formulas that we studied. N of A minus B plus n of A intersection B, n of B minus C plus n of A intersection B. Third value, n of minus n of A intersection B. This term will get cancelled with this term, same value, opposite signs, and these three terms will give you from the third formula n of A union B. What if we had three elements A, B, and C? Then here we will consider, let B union C is equals to D. We are assigning it another variable. So n of A union B union C will be equal to n of A union D. Now we do have a formula for this in two variables. This is n of A plus n of D minus n of A intersection D. Now we will resubstitute the value of D, n of A plus n of B union C minus n of A intersection B union C. N of A plus, here you can again apply the same formula of A union B, N of B plus N of C minus N of B intersection C. Okay. Here, what do you have? This is minus N of A intersection B. You can apply distributive formula over here. What does distributive formula say? This is N of A intersection B union B intersection, sorry, C into A intersection union A intersection C. This is your first term united with second term. First term union second term. Again, you can apply the formula of A union B over here, considering A intersection B as A and as the first set and A intersection C as the second set. So N of A plus N of B plus N of C. The rest of the terms as it is minus N of B intersection C minus first term N of A intersection B plus second term N of A intersection C minus N of A intersection B intersection A intersection C. Okay, so now we'll open the bracket, the rest of the terms as it is. Minus side will be introduced, N of A intersection B minus plus minus N of A intersection C minus minus plus N of, this is A intersection B intersection C, A is repeated twice in intersection. We know that A intersection A is equals to A. Also, intersection has commutative property. So this can be written as A intersection B intersection C. If you want, here's a detailed clarification. You can skip to the rest to the next page if you've understood this. For those who haven't, I'm giving you an explanation again. N of A intersection B intersection A intersection C. And this can be written as N of A intersection B intersection C. Here, B intersection C, A, has been written as A intersection B. We can flip it. Why? Because we know that A intersection B is equals to B intersection A. Because we know this, that's why we were able to write A intersection B. And here, we also know that A intersection A is equals to A. Again, another property of intersection. So, using this property and using both these properties, you can now write this is equals to N of A intersection B intersection C, the value that we wrote it here. So this is your RHS. This is the value of N of A intersection B intersection C. Next, there are some other formulas. A minus B is A intersection B complement. Now this we've already proven using Venn diagrams in the last class. So you should go back to that video for further clarification. For these two formulas, A minus B is equals to A intersection B dash. And B minus A is equals to A dash intersection B. If it is given in your question, A is equals to B, then what does this mean? This means that A is a subset of B and B is a subset of A. Now, apart from this, it also means that A minus B, you can also write this in terms of A minus B and B minus A. If A is equals to B, if both the values are equal, then by default, we can write A minus B is equals to B minus A. If we can write this, we can also write based on 6 and 7 formula, A intersection B dash is equals to B intersection A dash. So if A is equals to B, then you get 3 formulas or 3 conditions. This one, and this one. A, ninth formula. If A is a subset of B, then what does it mean? If you consider any element in capital A, set A, let's call it small a. Small a is the element which belongs to capital A. If you consider any element in A, then the same element will be present in B. This is definition of the term of the symbol subset of A. Subset of A and B sets. A is a subset of B. 10th formula, A union B. Now you can write this A union B in terms of set builder form as it is a set of all X such that X, let's consider it belongs to R, okay, and you're considering it real numbers, but this from this X, if X is equals to any number N, sorry, not necessary for you to have a real number, so let's just stick to this. Then X should belong to A. It's uniting them, so or X should belong to B. That means X should be belonging to either of the two sets. Doesn't matter, it's okay if it belongs to both the sets as well, but it should belong to at least one of these two sets, A and B. If you consider A intersection B, then it is a set of all X such that X belongs to A and X belongs to B. Now, when you say or, it means either of the two sets A and B. When you consider and, it means both. It's compulsory that this element should belong to both the sets A and B. This should be cleared. Next is symmetric difference of two sets. We already covered symmetric difference of two sets, but we didn't name it in the last class. So if you do remember, we considered two sets A and B. And if I shade this region, then we derived a formula for this in the last class. Now, the whole shaded region, whole shaded part, that means A minus B and B minus A, union of these two, is called symmetric difference of two sets. It's just a notation, and there's also a symbol to it. It's called A. This is a symbol, triangle type, A. This means there is a symmetric difference between A and B. It is the union of A minus B and B minus A. Next, idempotent laws. You already studied these laws. It's just, this is a revision part. Idempotent laws are A union A will give you A, and A intersection A will give you A. If you unite A and A with itself, you'll get A, and if you take the intersection of A with A, you'll get the same set A. Next, identity laws. What are identity laws? A union phi will give you A, and A intersection U. U stands for universal set. This U. A intersection U will give you A. So the common thing between A and U is A, and if you unite A with nothing, we'll get A itself. 15. Commutative. Commutative law states that A union B is equals to B union A in union, and A intersection B is equals to B intersection A in intersection. Associative law. In union, it would be, for associative law, you will have to consider three sets. We are considering ABC. So by default, the bracket will be solved first, but irrespective of which bracket you use, or even if we do not mention a bracket at all, the whole thing will be same. In intersection, it's the same. A intersection, B intersection, C. Both are associative in nature, union and intersection. Next, distributive laws. Distributive laws are A union B intersection C. A union B intersection C. Now, in algebra, it looks something like this: x plus y into z. In distributive law of algebra, you used to write x plus y into x plus z. Similarly, you will have to write over here A union. A is united with two values, B an intersection of the other value. So it will be exactly the same. A union B in one bracket, intersection, this intersection over here, A union C. A union C. What about A intersection B union C? Again the same. This could be analogically equal to x intersection is multiplication x into y plus z. We used to write x into y plus x into z. So either by analogy or by observation, A intersection B plus means union A intersection C. Formula: total number of subsets of a finite set of n elements is. So finite set of n elements, let's consider A to be the finite set. So the finite set that we're discussing is A. Finite set of n elements, it means n of A is equals to n, small n. To avoid confusion, let's consider it n instead of n. Finite set of m elements. The total number of subsets. So if n of A is m, then how many subsets does this set A has? We know that it is 2 raised to power n. We've studied this in previous class. It's just a revision, so it's restating the formula and writing it into a specific statement. Next formula is cardinal number or order of a set. Now this is also equal to the number of elements in a set, or number of elements of a set. It's just a fancy way of naming it. This is n of A. N of A is called number of elements of set. It gives the number of elements of set, or the order of a set, or the cardinal number of sets. Next, De Morgan's law. De Morgan's laws state that there are two De Morgan's laws. A union B whole complement is equals to A complement intersection B complement, and A intersection B whole complement is equals to A complement union B complement. Let's consider two Venn diagrams to understand the meaning of this. So for the first formula, A union B whole complement. A union B means this pink shaded region. If you want to take its complement, then you will have to consider, let's say, green region. This would be the complement of A union B. That means now we are only concerned with the green region, not with the pink region. Okay, so let's erase the pink region out. This is the green region is A union B whole complement. The right hand side states that A complement intersection B complement. So let's consider A complement first. You have two regions, two sets A and B. A complement means everything which is not in A. So the dotted region is not in A. B minus A part is not in A. So this dotted region. And what is B complement? B complement is anything which is not in B. It should be this region, the exterior region and this region. And what is common in this region? The region where you have both the dots as well as lines. So this region is not in common because there are only dots over here. And this region has only lines. So from these two Venn diagrams, you can see that the first equation is proved of De Morgan's law. Similarly, you can also prove the second equation. Again, no one will ask you the proofs of these two. It's just for explanation. You'll have to memorize these laws. These are very important laws. With this, we'll complete sets. In the next class, we'll start with relations and functions. If you have any doubts or if you have any topic that you think I should discuss in sets, let me know in the comments below. Thank you.